Hello everyone, I'm Yuni from Chinese Academy of Sciences. I'm going to talk about divide and conquer determinization of Büchi automata. This is drawing work with Andrew Turini, Weizhi Feng, Moshe Wardi, and Li Jinzhang. Büchi determinization is a well-known problem in automata theory. It's the problem of how to transform non-determinist Büchi automata into determinist omega automata with more general acceptance condition than Büchi, such as Rabin condition, parity condition, and the Emerson-Ley condition we consider in this work. The reason why we need more general acceptance condition is that Büchi automata are not closed under determinization. Büchi determinization is very useful and has found many applications such as reactive synthesis, probabilistic verification, complementation of Büchi automata, and their language inclusion checking. In fact, it's implemented in spot for checking language inclusion between Büchi automata, and it's already used by Pecan theorem prover. Büchi determinization is known to be very hard. We know that to determinize non-deterministic finite automata, we only need a subset construction, and it's only single exponential. While for Büchi determinization, we not only need a subset construction, but also need to define two pre-orders on the reachable states, which leads to the complexity 2 to the power of n log n. Here n is the number of states in the input Büchi automaton. The subset construction and pre-orders are often implemented by the Safra-Petermans tree. It's worth mentioning that existing works are all operating on the whole graph structure of automata at once, which is very different from our construction. In this work, we made the following contributions. First, instead of working on the whole graph structure, we adopt the divide and conquer methodology. We perform independent and specific determinization construction for each SCC in the input Büchi automaton. Second, by using our determinization construction, we prove that two subclasses of Büchi automata have better upper bounds. One class has complexity n factorial, and the other has complexity 2 to the power of n. Both are exponentially better than previous results. Finally, we have conducted comprehensive empirical evaluation on a large set of benchmarks and confirmed that our algorithm is practical. To start with our construction, let us see an example Büchi automaton on the left. This automaton has an initial state Q0 with subloops on all letters, and it can either stay at the initial state or transition to one of the Q1 to Qn state. The Qi state has self-loops on all letters except the letter I. Here, double arrows denote accepting transitions. We also have a sync state to make the automaton complete. We observed that for this automaton, the state of art2 spot and hour produce a determinist automaton with n factorial states. The reason is that the constructed automaton used up all possible orders over the states Q1 to Qn. That is, we need all permutations of those states to construct deterministic automaton. However, we observe that two different states Qi and Qj cannot reach each other because they belong to different SCCs. So the rounds looping on them will not affect each other. So there's no need to put an order on all of those states to distinguish those rounds. And this gives us the insight that we can just determinize each SCC independently. This leads to our divide and conquer determinization. We can create pre-orders for each SCC independently from other SCCs. The construction is justified by the fact that rounds in different SCCs will not affect each other. Inspired by previous works, we can further improve our construction by classifying the SCCs into three different types, namely inherently weak SCC, deterministic accepting SCC, and non-deterministic accepting SCC. In an inherently weak SCC, we require that all cycles are either accepting or rejecting. In a deterministic accepting SCC, the transition relation must be deterministic. And we classify all remaining SCCs as non-deterministic accepting SCC. By classifying SCCs into different types, we can determinize them with different and specialized constructions. We show that inherently weak SCCs can be determinized in exponential time. Deterministic accepting SCCs can be done in time n factorial. And for non-deterministic accepting SCCs, the complexity is the same as for general Büchi automata. This gives us the insight that we can leverage specific construction for each type of SCCs so to fully take advantage of their structural information. With these two insights in mind, we now introduce our final divide and conquer determinization construction. Given an input Büchi automaton, we first conduct SCC decomposition and classify SCCs into three different types. For each type of SCCs, we use their specialized construction to obtain a deterministic parity automaton. And then we compose those automata into a deterministic Emerson-Lake automaton with union product. This Emerson-Lake automaton will accept the union of the languages of those SCCs. At last, we can also transform the Emerson-Lake automaton into a parity automaton. To improve the performance, we actually perform the union product on the fly, and the details can be found in our paper. Now we are ready to give our main results. We show that our construction is correct and has the same state-of-the-art complexity as previous works for general Büchi automata and weak Büchi automata. We prove that for Büchi automata with only inherently weak SCCs and deterministic accepting SCCs, our complexity is only n factorial. This class is so far the largest subclass of Büchi automata with this complexity. If we put more restrictions on this class, like we let automaton have only one inherently weak SCCs and make deterministic accepting SCCs have one sinc state, we obtain a new subclass, and the complexity will be improved to exponential time. Both subclasses have exponential better upper bounds than before. We have implemented our algorithm in a tool called Cola, which is also a type of drink we like. It's built on top of Spot. We compare Cola with Spot and Hour. Spot implements the classical Safra-Peterman's approach. Hour implements specific constructions for inherently weak SCCs and deterministic accepting SCCs. As for benchmarks, we collect around 16,000 automata from literature, and we let all tools output deterministic parity automata because our only gives us parity automata. As for comparison, we consider the running time and the size of the output automata. First, we consider the number of solved cases in the given time limit. From the bar chart on the left, we can see that Cola solves 41 more cases than Spot and 154 cases more than Hour. Regarding the running time for each tool, we give their part 2 scores on the right. We can see that the score of Cola is much lower than those of Spot and Hour, which indicates that Cola outperforms Spot and Hour also on the running time, In fact, our results show that Cola solves more cases in a shorter time. Next, we compare the size of the automata produced by Cola and Spot. Here we only show the plots for the number of states because the results are similar for the number of transitions and the number of colors. Our plot is organized like a heat map, where the blue color corresponds to fewer data points, and the red color relates with more data points. Moreover, the points above the diagonal indicate that our constructed automata are smaller than those by Spot. We can see that this is the case for most of the points, which indicates that Cola very often produces smaller parity automata than Spot. As for the comparison with our, the results are similar, except that the advantage of Cola over our is much larger. We can conclude that Cola outperforms Spot and our also on the size of the output automata. So to sum up, we propose a divide and conquer determinization construction that performs independent and specific constructions for each SCC. With our determinization construction, we show that two subclasses of Büchi automata have exponentially better upper bounds than previous results. We also demonstrate that our implementation Cola outperforms Spot and our on a large set of benchmarks, which indicates that our algorithm is practical. We notice that we can determinize each SCC independently, so as future work, we believe that conducting parallel determinization for each SCC might further improve the running time. Moreover, we would like to apply our divide and conquer methodology in the context of reactive synthesis, probabilistic verification, Büchi complementation, and their language inclusion checking. That's all for my talk. Thank you for your attention.